All right, so so this session is going to give a quick demo about how to install and use XGen for optimizations of DNA models. First, I'd like to give a quick overview of XGen. XGen is an end-to-end deep learning optimization toolchain, and it has some modules for AI model compression, as well as a compilation module that can generate efficient binary code. Now, as an end-to-end optimization tool, it accepts users' requirements like latency, desirable accuracy, and also could include some existing training scripts for some initial machine learning models that could be optimized, and as well as users' distance as input to the toolchain. And then the toolchain itself runs on a GPU machine, and this machine could be equipped with some edge devices like smartphones connected through USB cables. And then this toolchain will automatically optimize the initial machine model and test them on the devices directly, measure the speed, eventually output the optimized AI model and the optimized AI code that can be directly integrated into users' apps. Now, with this overview done, we are ready to look at how XGen could be installed and used. Now, this is a terminal. It's actually a remote terminal on the GPU machine. Myself, I'm using a laptop, Mac laptop. I remotely connect to this machine. And then on this machine, I can already have downloaded the XGen installation script. So I will just run this script. And then the installation would get started. So this initially is a agreement, it's a accepts agreement, and then the installation process gets started. And we can execute XGen by giving it a name. This name is going to be used as suffix of the Docker for XGen. And now XGen environment is getting started. So this process will start several Docker images. So it will take maybe 20 seconds to get started. All right, so now we have XGen environment. And now we can just start running XGen. While XGen is being started, we can see that it checks some software license, and the license will be checked every time XGen gets executed. And now we are ready to use XGen to optimize DNA models. Now XGen the interface right now is a command line based interface. It will ask a series of questions to get the requirements from the user and preferences from the user. Now, the first question is, which platform device do you want to use? So currently, the system I'm using is like shown here. This is the GPU server I'm running XGen on, and it has a smartphone. This is an Android phone connected. Now S10, this is Galaxy S10. So here I'm going to choose Android device. And then this is the device model will be listed. XGen automatically detects all of the connected devices. And now next is to ask the user to choose the base DNA model to start with for the optimizations. Now in this POC, as we understood, so you are interested in YOLO-X model, so you could just pick the YOLO-X model. YOLO-X model here is the default YOLO-X model, the YOLO-XN installed within XGen. If you pick this one, then the optimizations of YOLO-X will get started. But it's because YOLO-X optimization will take a long time, to just show you quickly a complete demo, I'm going to pick a small model. Is this DigitNet trained on MNIST dataset. Now pick the base model, and then this base model is going to get optimized by XGen later on. But before the optimization starts, the XGen want to first download this base model. So the base model will be downloaded automatically, and then ask whether you want to use default dataset. If we have other own, if you have your own datasets, then you pick no, and then you can provide the data path for XGen. For this quick demo, I'm going to just use default MNIST, and the dataset will be downloaded. After that, XGen asks what options, what operations does the user want to do. Now for this model, for the compression operation, we have several choices: pruning, scaling, and PS. These are all detailed in our documentations. But in this, there are just different ways to compress a model, and XGen supports all of them. Now, for this model, for this demo, we are going to pick pruning as the compression method. And then next is the user's desired metrics for the model that should be produced by XGen. Now, right now, the primary interest could be either latency or quality score. In this example, suppose latency is the first order of consideration, and the desirable latency is 1.6 milliseconds per inference on the edge device. And then is the quality score. So it means if we have models, multi-models can meet this latency requirement, then what would be the quality score that can make the user happy? So here is, you could just put any accuracy or just the max. You want to maximize the quality score accuracy. XGen can automatically detect what GPUs are on this installed on this machine. Right now on this machine, there's only one GPU, so it shows just the one GPU. Pick this GPU to use for XGen to do all of those optimizations and fine tuning. And then there are some hyperparameters for the training and fine tuning, like batch size, learning rate, and epoch number. After that, so all of these can be changed by user. And then there are some other questions like, do you have a pre-trained model? If you have a pre-trained model of the base DN model, then XGen can automatically leverage that in its optimization process. But it's okay if you don't have it. As confirmed, we want to continue. And then is the work paths that you want to use, you want XGen to use to save all of those intermediate and final results of the optimization. So you could just let XGen to create one for you. So this is what we are doing here. And then we have already gave XGen all of the requirements and preferences. Now XGen starts doing all of these optimizations, trying to create a model that can meet the latency target as well as the accuracy target. And what we printed out on the screen are basically some settings for XGen that XGen automatically derived from users' input. And then it gets into the first out of 3 stages. It has 3 stages optimization. First stage basically is to pre-train the basic model. So because we don't have pre-trained models, it will just train the basic model on the data set. And after that, it will, after 3 epochs, it finishes, get accuracy 99%. And then it wants to measure the speed of this model, default model. This is the original model on the edge device. Notice that this measurement actually is using our compiler to generate the code. So it already benefits from our backend compiler, the code generation. Now, what it's doing here is it compiled the model and send the model, the code to the smartphone I showed earlier, and run it and collect the speed. The latency of this original model is 2.9 milliseconds, which is much longer than 1.6, our target. So XGen would start to get into the second stage, would try to start to do all of those pruning. So because we select pruning to do the pruning, this is second stage just trying to find the model that can get as close as possible to the target 1.6 milliseconds. So it found one that is 1.8 milliseconds on this edge device, which is close enough. So then it will try to get into the third stage, and we'll try to do all of those fine-tuning and further optimization of this model, and eventually so this is a fine-tuning process, and it achieves this is the first epoch. There are 3 epochs for fine-tuning, and it will report the accuracy, the final accuracy, as well as the latency to us. It'll take maybe another 20 seconds. Okay. Yeah, after 3 epochs, it already have the model fully fine-tuned. This model is very small, so 3 epochs is enough. But yeah, for some other, like ULX, for 10,000 images, this process could take several hours. But that is necessary because for DNA optimization, it usually takes quite some time to fine-tune the model. Now, this is compiling the model and then produce the code and then run the code on the device, and it measure the final accuracy. Final latency is 1.8 milliseconds, which is close enough to the target, a given target, and the quality score is 98.92% accuracy. Now, the model size, this here is actually the model size original model because we are using pruning, but this side shows the non-zero model parameters, which means because pruning would set lots of parameters to be 0 to 0, and it actually only needs to store non-zero elements. So this could be the size of the model, final model, which is much smaller than the original model. And finally, the XGen will tell the user where those output files, code, and model are stored. These are the paths. All right, so this is a demo of how to use XGen for optimization, for pruning and optimization of a model. Now, what I showed in this demo so far, it just shows use the basic model, use the default data set to do all of these optimizations. Now for ULX, this POC ULX exploration, you have your own data set, and you could have 2 ways to use XGen to optimize your ULX. Now, if your ULX actually is based on the default ULX M, and you want to just use your own data set to fine-tune the optimized ULX models by XGen, then you could just pick this ULX model here and then provide the data set. Now, the other way is you could just choose this option. If you choose this option, XGen will ask you to provide the path of your own YOLO-X model and training script. And then you can also provide some other parameters like data sets and so on. But I'm going to quickly just demonstrate how to use this with this option with customized data set. Now, if you pick this one and ask you, do you want to download this default YOLO-X model, which is YOLO-XM model, then XGen will automatically download it. And ask you whether you want to use the default data set. Now you want to use your own data set, you choose no, and then provide this data paths. So in here, so we actually already prepared a example data set with with 10,000 images. So I'm going to copy this data set here. So this for class 10,000 images. This is what we have prepared just for our own demonstration purpose. And if you have your own data set, you could just do the same. You put your data set into this folder. So XGen data. Yeah, so I think we can just skip this copy. Just do this decompression directly. So after this decompression, so the dataset will be ready to use. But one thing needed to be pointed out is for XGen be able to use your own dataset, XGen requires your dataset to follow some kind of structures, that which actually is detailed in our XGen document. Now we have this COCO 4, which has the dataset has about 10,000 images, and we can use this as the dataset. So within XGen, it is within this directory. So this is mapped to the home host directory as we saw before. And then put this as the data path and do the same for, because all of the training data set and the validation set are in the same data folder. So we just need to give the same data folder for all of them. And then number of classes is 4 for the classification. Now you can pick any of these options to do the optimization. So you could pick in here for YOLO-X, our recommendation is scaling, but you could use pruning as well. Later I'll show you some of the results we obtained in our own experiment for YOLO-X. Now then you can pick scaling as the compression method, and then specify your desired latency, and quality here is average precision, and then pick the GPU you want to use and hyperparameters, and we don't have pre-trained paths. Now XGen start working on this YOLO-X. So what it is doing right now is it actually downloads some existing YOLO-X models weights, and then ask, we have these two options for two mode for optimizations. One is faster, which is taking only one round of training time, but it may not find the best model. But this extensive optimization could take a longer time, but it could give you better results. So here we just, for this demo, we use extensive optimization, and then specify the default workplace for this execution. And now XGen starts working on this YOLO-X, and the optimizations will be based on the dataset that you provide. So it will take a long time, several hours at least. So I'm going to stop this process. Now that is what, how just show you how we can use XGen to optimize models based on the user's requirements. Now the output of those optimizations actually, like what we in the DigiNet, it print out these. This is I can show you briefly what is the output here. So for this in the first demo, so this folder has the generated code is stored here. It has library, XGen runtime engine, and this is the model files, and then it has the header file is included. So with these, then by following our documentation, so user will be able to use the results in Android applications or iOS applications by invoking corresponding APIs, XGen APIs. They can basically initialize the model and then call the model to do inferences. All right, so with that, we can take a look at some of those results that we have seen so far. This is the ULX optimization results obtained by XGen in our own experiments. Now we have the data set we used is the one I showed earlier, is 10,000 images extracted from this COCO 2017 image dataset, and it contains 4 classes. And the first 2 rows shows the default YOLO XM and YOLO XS, their size, and also the running latency. And the latency is for one inference on this cell phone, which is a Snapdragon 855 model. And these 2 executions are using the default model, and the compiler is an API, which is the one Qualcomm provide for running the models on their machines. And then using our compiler, our XGen's backend, the compiler, for the same model, 2 models, we could already significantly reduce the latency by several times with the same accuracy. Because here we are not really doing any compression, any model changes. Now with model scaling, then we can further make the model smaller, reduce it starts from the M, and then it reduces the model size and also make the model run even faster. Now the accuracy actually can be maintained very similar as the model ULS, which has the same comparable size as our optimized models. But we get even better speed. Now, using pruning, ULX pruning option, so the XGen can set many parameters to 0 without significant affect the accuracy. So the precision actually is quite close to ULS, but the model becomes a number of times smaller, and the speed actually is still comparable with ULS. So this pruning actually is sparse, so it can still maintain the comparable speed as ULS. So yeah, that's what XGen can produce for ULX on our end. So there is another feature of XGen worth mentioning. So during the execution of XGen, the status of this tool execution and also the detailed log information can be accessed through the XGen dashboard. Page 6. Yeah, so this is the dashboard, and we can log the sign in, and then for the first time, we just need to, the default password is admin, and see, focal pi 3, focal pi 3. And then on the dashboard, the user actually can see the real-time status of XGen and also the XGen's instances. Its status and the tasks that it has finished. So this is each is a session, is a task XGen has been working on. So for example, it shows 3 stages in the optimization and the status of it. And if you click details, it shows the control workflow and the time spent in each stage of the workflow. And then here, this is the detailed runtime log information of the execution. So if things actually went wrong, all of these logs could provide some useful information for figuring out the problem. And it also lists the devices that are connected with the XGen machine. And so in our case, it's a Qualcomm smartphone. So this is the status.